Assalamu alaikum everyone. Welcome to another discussion on our series on clinical laboratory instrumentation. What we're interested in today is X-rays. So we're going to go ahead with a brief historical background about what they are, how did they come into being. Then we'll look into the construction of the equipment. How are these X-rays produced actually? Then we'll shed some light on attenuation of the signal once it passes through a medium, passes through a subject or a body. How does the signal behave? How does it attenuate? And finally, we're going to look into image reconstruction. So forming an image from an X-ray is fairly simple, but when it comes to computed tomography, which is essentially multiple X-rays at different angles, so that's what we're interested in understanding, that how is an image reconstructed from multiple X-rays in the case of computed tomography. So we'll be linking up X-rays with CT and understand image reconstruction from there on. So X-rays were basically discovered way back in 1895 by Wilhelm Conrad Röntgen. So Röntgen was a professor at a German university, and he was working with cathode ray tubes in his laboratory. And one fine day, Röntgen observed a fluorescent glow of crystals. So he was able to see some crystals glow on a table near his tube. And before we move on to why he did that, let's understand the arrangement of his tube. So it was basically a glass envelope with the anode and cathode, basically electrodes encapsulated in it, and the air in that glass envelope or glass bulb was evacuated. So it was basically vacuum. And when he was able to apply high voltage to this, he figured out and he observed that the tube it just produced fluorescent glow on phosphorescent materials in his room. So, and he was fascinated by it. Of course, it was something unexpected, something not done before in history. So, and this material, this phosphorescent material in his room, they were quite a few feet away from his tube. So he concluded many things out of it, but the first and foremost was this was a new type of ray that was being emitted from the tube. And he also covered this tube with the heavy black paper, and he figured out that the ray would still penetrate through this paper, and he tried different substances, and the ray would still pass through different substances, different materials, and sometimes casting shadows of solid objects. So he was able to conclude that this is a special kind of ray which would not pass through dense, heavy structures, but would pass through soft tissues or soft structures. One of the famous experiments, or the famous X-ray films that he developed, were of his wife's hand, which is pretty famous in historic context, where he X-rayed filmed his wife's hand, and as you can see, there's a ring on the finger as well. Now, the bones in the ring, the metallic ring, they tend to appear as a dense structure, which is why X-rays would not pass through them, whereas the soft tissues around the bones in the finger would allow the X-rays to pass through them. So that was a groundbreaking medical innovation in terms of medical imaging, where the world witnessed some great novelty in research work, and that changed the course of medical imaging, especially in radiography. So that being said, let's further shed some light on the construction of the X-ray tube. We've understood how it's more or less a glass bulb with electrodes in it and in a vacuum chamber. Well, let's look at it a bit deeply. So on your left hand side is an overview of what the entire process is. The cathode filament is going to generate some electrons which are going to hit the anode, and then X-ray photons are going to be generated, and then they're going to pass through a filter and the collimator, pass through the body, and then get recorded on the screen. So on your right hand side though is a more detailed description or view of what happens in the tube, in the X-ray tube. So, and that is what we're interested in today. So let's look at the components one by one to understand what's happening, what is the role or function of each component in here. So first off, the cathode filament, it's negatively charged. The cathode filament is negatively charged, and it has an excess of electrons, and electrons accumulate on it. They get boiled off, they get a lot of heat, a lot of energy, because we are providing very high electricity, high electric current to this cathode, and as a result of which the electrons get enough energy to move or get directed towards the anode. There's an electric field in between the two as well. So, and this process is called thermionic emission. The rate of production, more importantly, the rate of production of the electrons from this cathode that get directed towards the anode here is directly proportional to the current that is provided to this cathode. So higher the current, more electrons hit the anode. As a result, the X-ray beam is stronger, and then you get the result with the higher contrast, or the intensity of the beam is very high. So that's one way to understand the importance of cathode filament. The other important thing is the high voltage electric field that has been set up, which obviously allows these electrons in the cathode to accelerate towards the anode. And this acceleration is important because it gives them very high kinetic energy. So if they come with a high kinetic energy and they collide with the anode, they're going to get converted into X-ray photons better, and the high kinetic energy gets converted into X-ray photons as well as heat. So the majority of this is heat, and there's some packets of energy in the form of X-ray photons. Another important aspect is that this chamber is filled with vacuum. Actually, air has been sucked out, so it's not filled with anything, it's vacuum. So, and that is important because you want to remove any obstructions in the path of the electrons hitting the anode. So there could be electrons from the air molecules, such as or nuclei from the air molecules, that of nitrogen, oxygen, even carbon dioxide. So you don't want your electron beam to get obstructed by those nuclei or those electrons, because if that happens, there's going to be scattering, and this beam would not be very nicely directed towards the anode. So it would approach the anode rather scattered, or approach the anode with very weak kinetic energy or very low kinetic energy, and as a result the strength of the X-ray beam that is generated would be very weak. So the vacuum chamber is important in that aspect. Also, the next important aspect here is the anode, which is referred here as the target. I'm going to call that anode here. Okay, and so purpose of this is to convert electrons that approach it with high kinetic energy into X-ray photons. So electrons collide with anode, and they undergo two kinds of phenomena for the X-ray photon generation. The first way to generate X-ray photons is that since they come with very high kinetic energy, they approach the anode, hit the anode, there's the deceleration. So this deceleration is as a result of this deceleration, the kinetic energy gets converted into X-ray photons as well as heat. But this mechanism is called the Brahms-Strahlung effect. So this is the Brahms-Strahlung effect. So that's one way to have X-ray photons generated. The second mechanism for the X-ray photons to be generated is that it's called characteristic radiation. So in characteristic radiation, what happens is that the inner electrons, inner shell electrons of the anode, they get knocked out of the orbit by the arriving electrons from this cathode. And those inner electrons are replaced by the outer shell electrons. Now, as a result of this, there's a packets of energy that's released. That is our that packet of energy corresponds to the wavelength, the frequency of that of the X-ray photons. So that's the second mechanism for the generation of X-ray photons. Number one was the Bremsstrahlung effect, in which we said that there is a deceleration of the incoming electrons because of the obvious impact that they're going to have when they'll hit the anode. Remember, in this impact, there's no knocking out of electrons. But in the second method of X-ray photon generation, the characteristic radiation method, there's a knocking out of electron from the inner orbit of the anode. And that the electron which is knocked out is replaced by an electron from the outer shells. So since that electron gets knocked out, there's a packet of energy that's released. And that is the X-ray photon, in fact. So moving on from this, and pretty much based on this, the deceleration that we have talked about in the Bremsstrahlung effect is proportional to the density of protons of anode. So, and of course, the density of protons of the anode, it could be tungsten, or it could be silver, it could be a metal. So anode is obviously a positively charged metal, but the filament is usually, I think, tungsten, but the anode would be silver. But the point in consideration here is that the density of protons in this anode. So if there's an anode with a high atomic number, it would have more protons in its nucleus, and of course would be more dense. So the denser the anode, the greater the deceleration of the electron beam, and if there's a greater deceleration, it means that there's a greater conversion of kinetic energy into X-ray photons and heat. So to sum it up, using an anode with a high density, or using an anode with a high electron cloud, or high basically electron, instead of electron cloud, we're more interested in their atomic number because of the greater size of the nucleus. So if we use an anode with a higher atomic number, with a very dense protonic environment, we're going to witness greater deceleration because those electrons are going to have a hard time hitting that anode. And as a result, the kinetic energy will get reduced more when they're going to hit. So that is going to mean that there's a greater conversion of kinetic energy into X-ray photons and heat. Also, since there's a lot of bombardment of electrons into this anode, the anode gets heated, which is why a typical way to cool it is to rotate it. So they're going to rotate this anode in either direction, represented by this arrow. So that helps it cool, as well as prevents the same spot from getting hit by the electron beam again and again. So that's one way to keep it cool. The other thing is that this entire arrangement is set up in a lead shielding. So it's housed in a lead box, in a lead shielding, and the reason for that is that you don't want an accidental exposure from the X-ray radiation to the operator or the subject. There's still possibility, even with the glass envelope, there's still a possibility that there could be some X-ray photons scattering away from this chamber into the atmosphere. So the lead housing or lead shielding is going to prevent it from. It's going to absorb those scattered X-ray photons, and is going to prevent it from getting leaked into the atmosphere and exposing the operator or the subject towards it. Also, you notice in the diagram on the left hand side is an aluminum filter. So this aluminum filter is the core purpose of this is that since there's a range of energies that are produced through this mechanism. There's a range of energies of X-ray photons that's produced, and we're not interested in the low energy X-ray photons. So because those low energy photons are not going to penetrate through the soft tissue. Remember, we want the soft tissue to be penetrated, and if there's not enough energy in those X-ray photons, they're not going to penetrate through the soft tissue. So it's just going to result in a higher dosage of X-ray to the patient, and the scan or the result of the X-ray scan that we're going to see is not going to be sharp enough. So the sharpness of that will be affected because those low energy photons are going to get absorbed in the soft tissue. So it might actually cause blurring as well. Obviously, you lose sharpening, be more blur, but more importantly, it's going to, from a safety point of view, it's going to result in higher dosage to the patient. So this aluminum filter is basically capturing those low energy X-ray photons and ensuring that only the high energy photons get penetrated through it. Okay, and then that is the collimator, of course, is ensuring that the beam is directed properly and there's not much scatter in the beam. So that's the function of the collimator. So altogether, in summary, what we looked at was a cathode filament. Its goal was to produce electrons. There's a high voltage supply, and there's an electric field set up to ensure the electrons are accelerated towards the anode. We obviously have a vacuum chamber to make sure that this acceleration or this electron beam that's hitting the anode is not obstructed by any air molecules. So and then they hit the anode, which is the target, and they hit it with high kinetic energy and get converted into X-ray photons as well as heat. But there are two ways for them to get converted into X-ray photons. We looked at the Brahms-Strahlung effect, and we looked at the characteristic radiation. The Brahms-Strahlung effect was about the deceleration, and the characteristic radiation was about the knocking out of the electron from the inner orbit. We also looked at the lead shielding, which was more or less about absorption of scattered radiation, and from safety point of view, very critical. And finally, we also looked at the aluminum filter, which captured low energy photons, and then the collimator, which was directing these X-ray beams. Right. So now let's have a quick look at where these X-ray photons belong in the electromagnetic spectrum. We are actually looking at this. Here's where they belong in the EM spectrum, with frequencies about 10 to the power 18, and then wavelength around 10 to the power minus 10. And obviously there's a band to it. These are not definite, there's a band to it, but that's where they belong in the electromagnetic spectrum. So what we see here is a graph of what I wanted to understand was the energy profile basically, or the intensity profile of the X-ray photons at different stages. So what you have on your y-axis is the relative intensity. On the x-axis is the photon energy. The wavelength is decreasing, as you can see. We are already familiar with E is equal to hf. So if the wavelength is decreasing in this direction, means the frequency is increasing, which means the energy is increasing since they're proportional, right? So that means that towards the low wavelength areas you would notice high energy photons. So this is actually high energy photons, and it's consistent because we're talking about photon energy. So we're talking about high energy photons here. So it's this region we're interested in, the high energy photons. So, and that is what we should see, that after our aluminum, before we get to aluminum filter, let's look at the leaving anode. This is what happens when it leaves the anode. There are photons of a range of energies with relative intensities, right? And they are, if you just look at the central part of the curve, here's where they are, right? So you see, after it leaves the anode, that's what the relative intensity is. Of course the intensity is going to decrease after every incident. After it hits the anode, there's going to be some scattering, so the intensity is going to decrease. After it leaves the tube, some photons are going to get filtered, they're going to hit the walls of the tube, some would pass through the window, so intensity is going to get wasted or get lost, or it's going to get decreased in that process as well. Then the low energy photons hit the aluminum filter, and then we lose some photons there as well. So that's why the decrease in relative intensity makes sense. This is why the bell curve is meant to decrease as it moves from one filter or one incident or one event to the other. But also notice that the center, which I've marked here with a black marker, the center of these bell curves tends to move towards the right. I'm sure you could notice this. There's a movement of the center of the curve towards the right hand side. And as they move towards the right hand side, you would notice that the right hand side is moving towards the right hand side, means they are at a higher energy. So even though the intensity is fewer of the X-ray photon beam, even though the intensity is fewer in the last profile, the one after the filter, after the aluminum filter, let me mark it with this. I'm referring to this. Even though the intensity is lesser after the filter, its average energy is inclined on the furthest right as compared to the previous two profiles, which means its average energy is higher as compared to the other two, as you can see on the x-axis. So this is at a higher energy as compared to these two. So the average energy, because the center of the bell curve is situated here, which is where the bulk of the photons are. So even though it is at a lower intensity, as you can see here, it's at a lower intensity, but it's at a higher photon, higher energy level. So that's what we are interested in. Also, interestingly, you could see that the Bremsstrahlung effect gives us a profile of photons that are relatively uniform. It's evident from this, from the curve here. But for the characteristic radiation, you could see these spikes generated. And those correspond to those events where the electrons get knocked out from the inner shell and are replaced by the electrons from the outer shell. And as a result, there's a photon. So, for X-ray photons being released. So those events are registered here in these spikes. You can see them here. So from that perspective, this is a very interesting curve. This is a very interesting demonstration of what happens after every event, after every filter. Also, these profiles that we see are different for different anodes. So these curves could probably be for one metal. For silver, it could probably be something like this. For another metal, it could be something like this. So obviously it matters what is the material of the anode, and based on that, the energy profile of the extra photons is different. We'll move on to the next segment now. Right, so on to the signal attenuation part, and this is what happens when the X-ray beam is in the medium, and it follows this equation I is equal to I naught e to the power minus mu x, where I is the final beam intensity, I naught is the initial beam intensity that's incident towards the subject, mu is the attenuation constant. It's about how much of the intensity does it reduce as the beam travels in that medium. So obviously this is medium dependent. It's going to vary from one medium to another. And then X is the thickness of the tissue. Obviously thickness of the tissue is important in understanding how much attenuation is there. The thicker the tissue, the greater the attenuation. The thinner the tissue, the lesser the attenuation. So it follows this arrangement. What I've done here is I've set up a problem where incident in beam intensity is we're going to take it in electron volts, 20 electron volts. The attenuation coefficient of the this medium is 0.3 millimeter inverse, and the thickness is 5 millimeter. Notice that in the power exponential, the millimeters, the distance units are going to get cancelled out. So then the resultant intensity that we're going to have should be in the same units as is the incident intensity. So you'll get the final beam intensity in electron volts as well. It's a negative exponential, so it's a decreasing exponential. You should see the final beam intensity to be lesser as compared to what was incident. And so, the reason for that obviously is that it gets attenuated, gets absorbed in the medium. So that's one problem for you to solve. There's another problem set up along the same dimensions. Give this a try, and after the class, in our question and answer session, we're going to discuss more on this. There are two mediums now, and the orange medium is exactly half of what the blue medium is. So if the blue medium is 5 millimeter, the orange is going to be 2.5 millimeters. So that's the thickness of the orange medium. So give this a go. Let's see how it goes, and then we'll discuss it after the class in the question and answer session. The final topic of discussion today is image reconstruction. Now, I said earlier we're going to link this with computed tomography, so let's give it a go. So key difference between the two images, as you see them right away, is that one of them is a two-dimensional image, whereas the second image is giving more information in the third dimension as well. So I'll make this clear. This is an X-ray image, whereas this is what you get from a CT scan. A simple way to understand a CT scan is that it is multiple X-rays taken at different angles. And when those images or those multiple X-rays are reconstructed back, they give you a nice CT scan image. Essentially, it's just an X-ray source, as evident here. and then there's a ring of detectors, and then the X-ray source could move, and the detectors would capture those X-ray images, and when those images would be reconstructed together, that's how we form a CD image. Now we're going to look at a reconstruction technique, a fairly simple one, which is through the help of the radon transform. Now the radon transform, before we understand exactly what the radon transform is, let's look at the equation of the line. Y is equal to x plus b. Another way to represent this line is x cos theta plus y sin theta is equal to rho, where theta is the angle of the vector that is perpendicular to the line from the origin. And when you look at the radon transform, this is exactly what's happening here. Remember that if you go back, you would figure out that this is a delta function, an impulse function, and then here is f of x, y, and our sample, our subject, is a function of space in x and y, and what we are interested in is sampling this specimen at different thetas. That is what we are doing. Remember from an earlier class, an impulse at x minus 5 is essentially will exist only and only if the argument equals 0, which means that x should be equal to 5. That is where the impulse is going to be existing. So this is what it tells you. This is how you would interpret an impulse function. Right? Now have a look at this exactly the way from the equation of the line that we had. Now if I were to say x cos theta plus y sin theta minus rho equals 0. Now remember, this is still the equation of the line, but you put this in the impulse function as we have placed it here. This essentially means you are sampling your specimen only at this particular line. So that's, in this case it's this line, but in this case it's this line, but for different thetas it could be for different lines, right? Or for same thetas and different p's it could be multiple lines. So that's one way to understand the radon transform, that it's taking these different lines, which we call projections, because we call them projections because they carry some information, because they are impulses essentially. And if you look at, so these are different, we call them projections because they are impulses, their magnitude is 1, their coefficient is 1, so that's the magnitude, so they just get multiplied by our specimen. So they carry the information of the specimen at that particular x and y, at it or p or rho and theta. So they carry that information because their magnitude is 1, 1 gets multiplied by our two-dimensional specimen, we get the specimen back, but we get it at a particular theta. And so we are interested in getting multiple of these projections, and as a result what we get is information of our 2D signal, our 2D specimen. So that information is essentially in this projection, or in this complete projection for one angle. So these are individual smaller individual projections that contribute to one projection or one profile at a particular angle theta. So for this particular theta k, this is the projection that we get of this specimen. And a point in the projection, now if we just go ahead and focus on this key description here, a point in the projection, any point here, is the ray sum along this, which is the equation of the line. So if I were interested in a point, in what would be my value if I were to compute my projection, and I was interested in these points. Obviously these are basically getting sampled from our signal. So basically what this is doing is, what this equation is doing is, it is helping us get the value of these points together. That's what we are doing. And if I were to integrate, or basically just sum this particular, along this particular point in projection, I would get a value of my projection at this point. And getting similar points is this, I could draw a profile. I could get a projection at a particular theta. So once I have a projection at 1 theta, I could move my detector and my source for another theta, and then for another theta, and similarly I could do it for all 360 degrees, or I could skip some angles if I wanted to. But getting different angles, getting projections for different thetas is going to help me in understanding what the original image is. How does this exactly happen? We're going to learn this with an example. So let's move a little forward and see what this example has to tell us. What I have on the left hand side is a sample. It's a specimen, and if I am to, I'm going to go ahead and arbitrarily just look at some of the projection. Let's look at some at some theta. Let's look at theta 0. Let's call this theta 0. When I go ahead and draw projections at this theta, what should my profile look like? I should have nothing here. But then when I sum along this projection, I have ones here, but I don't have 0 there. So there's obviously some magnitude. And then I have ones here, and then obviously when I'm going to sum all the values in this column, I'm going to have ones here, so it's going to be higher than this. Similarly, when I do it along this column, I'm going to have a projection value about here, and then here, and then nothing again. So essentially my profile is going to look something like this. I do this again for another angle. This time I do it along 90 degrees. What is going to be my profile along this time around? It's going to be pretty much similar. 0 here, some value around here, a little more around here, some value there, and then absolutely nothing there. So it's going to be around like this. And then I could do it for 180 degrees and again 270 degrees, and I could get 4 projections. But each time I get a projection, I could go ahead and stack it up in another column like this. So if I were to stack my projection, this projection right here for one angle, and if I were to stack my projection for another angle right here, for the green one, and I could do it for all of them. What I get in result is a sinogram, and that is called a sinogram. Through this sinogram, we're able to reconstruct or get an idea of the shape of the original object. A sinogram for a circle would look something like this. A sinogram for different shapes would look something different, but for each angle that we, or each reconstruction, or each projection profile that we get, there's a corresponding image information that we can access, and therefore reconstruct based on that. So at each angle, if you did not, I'm assuming you did not have the information about the original image, the image on your left hand side, and I would only give you a sinogram on the right hand side, you would vaguely be able to tell that since each projection is similar in magnitude as well as in their size, it is more likely a circle. So you should be able to tell that, okay, this is a sinogram for a circle. Similarly, we're going to practice different shapes, and here's another one. This is still a circle, but this sinogram is different because this circle is situated slightly towards the left hand side. So what that happens is, for 1 theta, the projections look slightly different than they do for another theta. As you should be able to tell that a projection would look like this, slightly centered on this hand side, but when you look at it here from a 90-degree perspective, these projections would probably be centered. Oh, that looks horrible. Projections would probably be centered like this. So you could see when you stack these projections up, one of projection at one angle is towards the left hand side from the center, whereas in another projection your information, or the bulk of information, is at center. So that is what we try to do. If it is probably centered here, this is probably the green, the orange. This is probably the orange projection, and the green projection is probably this one, which is centered slightly towards one end. So that's one way to understand how image reconstruction works with the help of radon transform. So you get a radon transform, you could perform inverse radon and get the original image back.